fine.
Okay, so
Continue.
first question I see, Mir Bhaiya. So first question we see, is the error decrease in backpropagation? Yes. The why do we do backpropagation is basically to decrease error and to find out the right weights. So you understood, right? If we give the right weights to our network, then if we give right weights to our network, then obviously we'll get the minimum error, right? And this whole thing is done in backpropagation. So yeah, the error decreases in backpropagation. What is the need of weights? Basically, as I told you earlier in the first recap, that weights are basically a way of telling how much weightage a particular input has in our final output. So that is basically weights. It signifies the weightage of a particular input in the final output. So I hope your doubt is answered. Then dummy variable creation, I didn't get what this question is. Other questions? Yeah, as Raj has calculated this, the parameters that we said, 28 by 28 into 32, that those were the weights, plus we add a bias, and that's how we got here 2512.
Yeah, I guess Ankit, there's one more question in Q&A.
And that's how we got this number. Any more questions? Does number of epoch also plays a part in finding right weights and biases, or it's just neurons? Actually, just hold on to this question. Once the session gets over, we will the code again. We'll run the code that will answer this question, finding the right weights and or the neurons. So yeah, also finding the right weights does play is an important role, and it helps us in finding the right weight. But the whole question we'll answer at the end, because there's some part of the code which we are going to keep, and that may answer your question. Any more questions? K-fold validation. Not K-fold. We are just. It's not K-fold. Vanishing and these things, vanishing and exploding gradients, would be explored in the later session. Yes, SGD is what you said. Stochastic gradient descent. You will see this in the next session also. So don't scare the attendees here. It's good. Can you? Yeah, we will be sharing the notebook. We'll tell you if we are going to share it. And then what? How to decide number of neurons and hidden layers? How do we decide number of neurons and hidden layers? Basically, it is a hit and trial method. As we solve a lot of these neural networks, we just have to initialize randomly, and it happens with experience basically. For the regression classification, how will construct your layers in the sense what? Okay, we got one more question here. Is validation
so as you guys know, what is a validation split? Basically, what is validation data set in the first place? So what we do is, first of all, we take our entire data and divide it into training data and testing data, right? And training data is the thing which is visible to our neural network, and for the training data, the neural network knows what the outputs are, and it learns based on that training data. But now you need to learn the concept of what actually validation data is, right? So what we do is, we take some part of training data and call it as a validation data. And let's say first you trained your neural network on the training data, you got some error and you got some metrics for accuracies and stuff, right? And then you got to know maybe changing the neural network weights some way will increase our accuracy, right? So if you knew these things earlier while training, you could have changed those things while training only, right? So that's the thing. What is validation split is, what is validation data is, we check how neural network is performing during its training itself, and that way we make our further decisions, whether how to have parameters and which hyperparameters is working the best. Because the thing is, we cannot use testing data to change hyperparameters. It's like cheating. Like you already, it's like basically you're using you can just use training data to make whatever decision you have to make on your model, and you cannot use testing data to further change the neural network, because that way, it's like cheating, because it's like exam. In exam, before exam, you can just refer to all notebooks and online resources available to you, but during exam you just have to do what you have learned, right? So that's the reason behind using validation data and using validation split. So in that analogy, validation split is like, some portion of your exam that is already going to come in the exam, right? You already know few things. So that's validation split, validation data. And validation split is basically how we distribute the data, like how much percentage of training data should be for validation. Yeah, any more questions? Yeah, great. Yeah, one thing you have to remember as a it's an important concept from data science is, let I just cover right now, that you cannot make decision based on testing data, because testing data, the main purpose of it is just to evaluate how your model is working, but you cannot go back and change things based on testing data. And that's why validation data is for, where you can change things based on validation data, but you cannot change things based on testing data, because testing is just to find accuracy of how model will perform in real life as well. Okay, so I guess that answers your question. Are there any more questions? By the way, one of you just asked, like what is the need of weights? I think this question was asked long back, but let me just get back to the essence of it. Why are we doing all this in the first place? Why are we doing this stuff? What is neural network? Okay, so the reason why what is our aim? First of all, our aim is that if we have some data, we should be able to predict some data in future. What do I mean by that? Like, let's say let's say for example, let's take example of stock price. Let's say if I have some data of stock price, what has happened in past, and if I am readily able to predict what can happen in future, then it will be good for me, right? I'm using that data to my profit, right? So the reason why we are doing all this is, in the end, we have some inputs, we have some outputs. And what basically a neural network is doing is trying to make a function f of x that maps these input to corresponding outputs. And then all these things come, like how good it is mapping for mapping the inputs to outputs, and we rate it in terms of accuracy and stuff. So in the end, the essence of neural network is that it is just a function approximator. Okay, it is a universal function approximator, and it takes shape of any function. And how do we make a general function? We need to have some variables in the function that we can tweak, right? So let's say we have x square plus y, ax square plus by square, right? So a and b are really important in this case, because they I guess they define whether the graph would be circle or ellipse or hyperbola or something like that, right? So that way we are changing a in and b in such a way that it will approximate our data in some way, right? Okay, so that's the essence of neural network. It's in the end, it's just a function. And I just have a recap once what all Sanket said. So what is a neural network? It's just a function. We have an input, we have output, and we're trying to find a f of x that matches this input to outputs, right? So and how we get this f of x is by training. What is training? Training has complete three parts. First is forward propagation. What is forward propagation? Firstly, we just pass input to a random function and see what outputs it is giving out, right? Depending on that outputs, like initially if the function is random, the outputs will also be random, right? And depending on that output, we check what correct output should have been there. And depending on the difference of those, we calculate some error. Okay, we can find some error. And then next step is, first step was forward propagation, which we did just now. Second step is calculating error. Next, then last step is back propagation. Now what we do is we take this error and we find the individual contribution of each weights for that error, using the formula that Sanket had just mentioned, delta E by delta W. So for each weight, we find what's the how much error is the given weight contributing to the final output, and we update the weights accordingly. And why are we updating the weights? Because we have to reach that perfect function that approximate our input to output. And why weights? So as Sanket said, first we calculate error with respect to different weights, right? With respect to different weights, we find errors and stuff. And what we want is, we want to find such a weights that is giving us a minimum errors, right? Minimum error, such weight and biases that give us minimum error. And for finding the weights, for finding such weights, what we do is initially plot a graph between weights and weights on x-axis, weights and biases, and error on the y-axis, let's say. And what we do is initially we take a random weight, and using gradient descent method, we try to get to the global minima of the weights. Okay, and okay, I guess guys should have gotten this question as well. Given an equation, like let's say we have a graph and we want to find a global minima. We can find the global minima directly, right, using normal method for in calculus, like making gradients to 0. But why didn't we do that? Why did we use gradient descent? So actually, would anyone like to answer this question? To minimize error, why error with respect to weights? Why did we use gradient descent method? Why didn't we use normal derivative equal to 0 calculus method? Okay, I guess you guys had a lot of calculus today. So, so the main reason for it is normal gradient calculation method. Yeah, exactly. Faster computation to save time. So normal method for calculating minimum gradient is very time consuming. Time consuming in terms of, like, you guys might have learned in, if you're a CS student, you can find time complexities of algorithm, right? So the algorithm for finding minimum weight based on the calculus, that is gradient equal to 0, the time for executing this algorithm will increase more faster with respect to input size as compared to gradient descent. So basically, the gradient descent is much faster when the dimensions of input start to increase. That is, dimension of x start to increase, the gradient descent becomes very faster. So that's just the gist of it, that uh, uh, how our training takes place. First is forward propagation. We take inputs, we get some outputs. Initially it's random, so it won't be correct, and we find error. Then second step is finding error. Then with respect to error, we back propagate, and third step is back propagation, in which we update all our weights and biases such that error is a minimum than previous value. In such way, we try to minimize error until we get to that global minimum, and we do this using the gradient descent method. And then you just saw the code for in Keras. So as you guys know, if you directly use Keras library, you wouldn't need to deal with all the maths behind it. But as you are in a DSC workshop, we thought now it is more important to focus on maths of everything rather than the code, because Keras is actually very easy to implement, and you need not to deal with any of math or calculus, right? As you just saw in code, you just have to select optimizer, you just have to select algorithms and pass it to the Keras code, right? And it's simple, as simple as it is. And you just have to give the epochs and number of times you have to update weights and all that stuff. So I guess that
Here, there's one more question. Like, output layer activation depends on, like, how do you decide the sequence of activation function? So basically, suppose at the output we want something like values as 0s to 1. Suppose we want some value between 0 and 1. Then we'll try to use sigmoid function, so that the output, what sigmoid will do is that it will give an output between 0 to 1. So if it depends upon what output we will need, and most of the times what we do is that we try to use for hidden layers. or tanh or functions like we generally don't use sigmoid. We try to use ReLU and tanh or functions like this because of faster computation, so that we get faster results. And mostly it depends upon the output, what output we need. Is neural network interpretable or is it black box? I mean, can we see weights in between? We don't really see. First we just matlab, we initialize some weights. Okay, we can check what the weights are at a particular iteration, so we can see the weights because every time weights get updated in a particular iteration, we can say what we can see, what the weights are, what the biases are. We can see this, so it's not like a black box.
Yeah,
Anything?
actually, if you like, that's a good question. Actually, can you see the weights and biases? And you don't actually need to see the weights and biases once you decide what all algorithms you are using. And like I just recently saw a few posts on Google AI's team, that they actually hire people for like they call it an explainable AI, and they actually hire people to, what they do is first make an algorithm, any algorithm, let's say Google translation algorithm, and first they make it work using our all these methods right now just we saw. And after making them work, they have a special team to figure out why actually it worked in the first place, like which layer is doing what, why this neuron had this value, and why giving this input. They have an entire team just to explain why it worked. So that's actually important thing you pointed out, that we don't need to see the weights once we have finalized what our algorithms is, and how are we going to optimize it. Like let's say we are using gradient descent to find the weights and biases such that error is minimum. Then the algorithm will iteratively just update all the weights and biases itself till the number of epochs you have mentioned, and it will stop. So that way, if you want, you can like check it out, but you don't need to see. So are there any more questions?
Question it says that why is it really preferred, I guess. Okay, so you saw that in sigmoid we had to calculate 1 upon 1 plus e to the power minus z. This is a time taking computation, right? Whereas the ReLU, what will it do is it will, if it's a positive value, it will give that positive value, and if it's negative, it will give us 0. So basically this increases computation, and so that it just increases computation so that we get faster results. So there will be faster iterations, faster changing of weights. So that's why mostly we use ReLU.
Yeah, I guess guys, please put your questions in Q&A, because like it gets difficult to find where the actual questions are, so it will be easy for us. So I guess now you guys might have been very tired, and it must be a lot of calculus for you, because trust me, but I understand you, and I can because at the first moment even I was like really overwhelmed by the calculus, but this is just a one time. Once you know what's the construction of neural network, and then everything else would be easy for you. So now just as a refresher, do you guys want a refresher? So right now we have planned a online game, and it's a bit surprise. First, let me know if you are ready for it, and do you actually want a refresh. Is the recording going to be shared? We'll let you know later. Yeah. Is there any chances of neurons getting updated with weight 0? If yes, then what would be the steps we need to take? Yeah, so as that's a good question. As Sanket had just mentioned, how do we initialize weights? Sanket, would you like to take over this question?
Sorry.
You for a
is
new
there
type.
chances of neurons getting updated? No, actually what would happen is that if we initialize the weights to some constant value, all the weights to a constant value, then all the weights would get updated again with some constant value, right? So basically what it was w minus some differentiation dw that we did. Then just you think that, to this formula we have lots of weights and we are this is the same formula, right? It's basically 5 minus 4 for all of it, like lots of 5, lots of weights have, all the weights will be having some constant value, suppose for example 5. Now what we are doing is that we are updating again with some constant value, so the weights would get updated in the same manner because the uh, equation is same, right? W minus some dw. So all the bits would get updated in the same manner. So that's the loop, right? First it will be 5, then it may get updated to 4, 1, then again some minus negative value. So all the weights will stay constant again and again. So it's just kind of a loop.
Yeah, and I guess that answers your question. Yes, is asking how can all this process be visualized. So just wait for it for some more time.
Yeah.
We are going to actually show you the visualizations. It's a software. It's a website called TensorFlow Playground, and it will actually visually show you what is happening to each weights and what is happening with each neurons. Okay, so just wait for it for some time. Could you please suggest some resources? Yeah, we'll definitely suggest you resources. Right now, we'll not just right now. We'll come back to that as well. Okay. So yeah, TensorBoard. Yeah, TensorBoard is also a thing. Okay, you can visualize your own models by using that. But yeah, what is recommendation for doing ML and AI? Okay, I guess I'm not the right person to answer that question. But as Nitesh sir said, your branch doesn't really matter actually, and the resources for ML and AI are available all over the internet. As you guys like know already, some of you know, Three Blue One Brown, great YouTube channel. You can follow that. Other is Andrew NG courses. Most of you might be already familiar to it. So yeah, you can learn anything online right these days. Okay, so and AI's topic, it is actually has too many resources available on. You can learn everything on your own. So yeah.